Hello everybody and welcome to the Latin American webinars on physics. I'm Nicolas Bernal from the ICTP Safer in Sao Paulo, and I will be the host of this second webinar of the second season. Today we'll have a great talk which is in the line of Axions and the Relaxion. But before to go to the talk, don't forget to ask questions via the Google Plus Q&A here, or via Twitter with the hashtag LAWOK. So the speaker today is Lorenzo Ubaldi from the University of Tel Aviv. Lorenzo obtained his PhD in the University of Santa Cruz, California, and after that he realized a postdoc in the Bonn University, and now he's postdoc in the Tel Aviv University. And the title of his talk is the Relaxion. Is the Relaxion an action? So, Lorenzo, are you there?
Hello. You can hear me, right?
Very good.
Hi, everybody. Well, let's see. So now I have to share my slides, I guess, right?
Right, please.
Let's see. Can you see it?
Very good. Please go ahead.
Okay, good. Thank you, Nicolas, for the introduction. Very nice of you. I don't know if this talk is going to be a good talk. You guys will tell me at the end, I guess. It's crazy to me that I'm talking in front of my laptop and I have no idea how many of you are out there. But okay, let's see. We'll see how this goes. So this is some work that I've done in collaboration with these people at the Weizmann Institute, and they are Rick Gupta, who is another postdoc there, Zohar Komardovsky and Gila Perez, who are two professors there. And the paper is recent, so we put it on the archive at the beginning of this month. And I guess without further ado, I will just go into the slides and what I have to say. Okay, so to begin with, oh, by the way, Nico, you can interrupt me, I guess, if you don't hear me anymore or something, right?
Sure, I will do it.
Okay, great, thanks. And also, you told me that there are no questions during the talk, but if people are willing to ask questions during the slides, I'm totally happy to take the questions also during the talk, no problem. Okay, so that's it. I wanted to start with a review of what this cosmological relaxation mechanism is about. So this is an idea that these people, Peter Graham, Kaplan, and Rajendran, have put forward a few months ago. They put out that paper in April, I guess. And it's, I would say that it is genuinely a new idea of how to address the hierarchy problem. And so first I want to go somehow through the details of the mechanism, and then I will have, you know, some complaints, if I can say so, about some basic ingredients of their model. So here you can see in this slide the Lagrangian that they use in their paper. I use slightly different notation actually, because in their paper the coupling G is dimensionful, whereas I defined it to be dimensionless. So their coupling G is just my G times capital lambda. This capital lambda that you see here is the cutoff of this theory. So you should think of this Lagrangian as an effective field theory. And now you see that pretty much the key point of this game is that you make the mu squared term, the quadratic term in the Higgs potential, you make it a dynamical quantity. So this mu squared now depends on the field phi, as you see on this slide. And the other crucial ingredient is that you need the potential for this field phi that is written here as an expansion in G phi, pretty much. So you have a linear term and you have a quadratic term. And this potential is pretty much responsible for phi to roll, okay? Phi will roll during inflation. I will get to that in a second. Another point is that as phi moves along field space, it scans the physical Higgs mass. So the idea is that you start from a point where the mu squared term is positive, and as phi keeps rolling down its potential, it will reach the point where this mu square will become negative. And when that happens, you know that you get into the broken phase, which means that the Higgs field develops a wave, and you are in the broken phase. Now, another important term is the last one that I have on the first line, which is the coupling of this field phi to GG tilde. And GG tilde is the, G mu nu is the field strength of SU3 color, okay? So what happens, because of this last term on the first line, when you go below the QCD scale, so when you go below the confinement scale of QCD, this term generates a cosine potential for the field phi. And you can go through, the whole song and dance of either computing like this potential through instanton effects, or you can compute that via like means of chiral Lagrangians. And what you find at the end of the day is that this cosine potential which is generated is proportional to the mass of U, or the mass of D, actually, in this case, times F pi cubed. So you see that it's linear in the quark mass U, which means that it generates a potential which is linear in the Higgs wave, okay? This V right here. Now, this potential is crucial because this is what is going to give us a back reaction to set the electroweak scale. So a cartoon of how the mechanism works is the following on this slide. So you have this potential, as I told you. It's linear up here, pretty much, okay? And the linear part continues all the way down. But the thing is, once you hit this point where the field phi is equal to lambda over G, you start developing this oscillating potential, the cosine potential, right? Because so this is the point where the mu square term of the Higgs becomes negative. And below this point, you generate this cosine potential, and so you start having these wiggles. And now the other important part is also that you see that these wiggles, this is just a cartoon, okay? So it's totally off scale in a way, but it's just to give you an idea. But the point that you can see also from the cartoon is that the wiggles start small because the amplitude of these cosine oscillations is proportional to V, and V becomes larger and larger as you move to the left here of phi, right? Because as phi moves to the left, the mu square term becomes more and more negative, and the Higgs wave becomes larger and larger. So as that happens, these wiggles grow, and at some point, they grow enough that the rolling of the field phi is going to stop. Okay? So I put here the points 1, 2, and 3, and as I told you, you start from very large field values, okay? Values larger than lambda over G. Remember, lambda is the cutoff of our theory. Then the field rolls down the potential, and it rolls down very slowly because this whole process happens during inflation. So there is some Hubble friction, which is keeping the motion of the field very slow. And this is very important, actually, because if it wasn't for the slow rolling, the field wouldn't stop at this wiggle. It would just keep rolling down, okay? So it's important that the mechanism happens during inflation. And then, as I told you, so when the rolling stops at this point 3, we pretty much, at that point, we have, again, this is totally out of scale in this plot, so don't look at the field space in phi. It's totally out of proportion in a sense. But the point is that you stop on a wiggle, and at that point, you're going to have mu squared, which is much smaller than lambda squared. If you achieve that, that's pretty much a way to solve the hierarchy problem, because it is a way to say why this mu square parameter in the Higgs potential is so much smaller than the cutoff. So in principle, if you wanted to solve the hierarchy problem, you would like to push the cutoff all the way to the Planck scale. Okay, if you could do that with this mechanism, you would have totally solved the hierarchy problem. Now we will see that actually in most models, the cutoff, in the original papers, they claim a cutoff of 10 to the 7, 10 to the 9 GeV, depending on the model, so you don't quite get to the Planck scale. Okay, so I want to list some of these conditions that you need during inflation. So first of all, as I told you, it's important to have slow roll conditions. Okay, I'm not going to go through the derivation of these inequalities here. I'm just going to state them. You can find kind of a derivation for them in the original paper, but not really. But anyway, they're not so hard to derive. I will tell you qualitatively what they mean. So the first one is easy. It's a slow roll condition. So you're just asking that the speed of the field phi, or the kinetic energy, is much smaller than the change in potential energy, pretty much. Okay. And it gives rise to these two conditions. And they will be trivially satisfied, actually, if you satisfy the second to last condition here, which is the classical bits quantum. I will get to that in a second. Another important condition is this number of e-folds. So this condition comes about because pretty much you want inflation to last long enough so that the field phi has enough time to scan the whole field range, the field range being this lambda over g. Okay? So if you go through this condition, you find that the number of e-folds has to be larger than this quantity. I should mention, because this is important, that this capital H with the subscript I is the Hubble rate during inflation. Okay. Another condition that you need to satisfy, you want the vacuum energy during inflation to be dominated by the inflaton field, which I haven't even written in the model. Okay, it can be whatever. You will have an inflaton that will drive inflation, and you want to make sure that the field phi, which is the field that rolls for us, doesn't dominate the vacuum energy. In other words, you want to make sure that phi is not the field that drives inflation. Okay, pretty much the reason for this is because at the end of the day, you want phi to be stable. So you don't want it to be the inflaton. The inflaton will have to decay. Okay. Then there is this other condition that they call actually the condition that the barriers form. By the barriers, I mean the wiggles. So pretty much, in order to generate this cosine potential, you have to go below the confinement scale. And maybe a better way to write this inequality, instead of writing as I did, and as they did also, hi less than lambda QCD, maybe it would be better to write like the inverse, like saying that 1 over hi is larger than 1 over lambda QCD, because you can think of this in the following way. You can think that 1 over hi is pretty much the Hubble radius during inflation, and 1 over lambda QCD is like is the length, is the confining length of QCD. So if the Hubble radius was smaller than the confining length, you wouldn't have confinement. If you don't have confinement, you don't have instantaneous effects, and you wouldn't generate the cosine potential. So that's why we need this condition too. And then the last condition, which is actually not strictly necessary in a way, it helps with the game, is that the classical rolling beats the quantum fluctuations. So for this, you can have again in mind, if you think of inflation, for instance, let's think for a second about the inflaton. In the inflaton, you have this inflaton field, which is slowly rolling down its potential, okay? And at each point of the rolling, if it rolls down too slowly, you don't know exactly where the field is, because there are quantum fluctuations around the point where classically the field is. Okay, the same is true for our field phi. So as it rolls down, if it rolls too slowly, there would be quantum fluctuations that tells you, okay, maybe the field is not exactly there, but it could be slightly to the left or slightly to the right. And okay, in principle, this is fine, but in practice, it's nice to impose this condition, which just tells us that the rolling has to be slow, but not too slow, so that it's pretty much dominated by the classical rolling. So that once we stop, we know exactly where we stop. Okay. Whereas if there were quantum fluctuations, you could say, oh, maybe I stop in this wiggle, maybe I stop in the next one. Okay, so it's just for convenience, let's say. But in principle, it could be relaxed. But let's keep it. It's okay. And then the crucial condition, which is the one that actually, at the end of the day, sets the electroweak scale, is this last one. So the condition for the rolling to stop is given by setting the derivative of the linear potential, which is in VG phi, equal to the maximum slope, the maximum derivative of this oscillating potential. Okay? It means that at the point when the slope is flat, the field is going to stop, because it's rolling so slowly. So when it gets to the point, it will stop. So from this last condition, you get this equation here, which tells you that g times lambda cubed f is equal to lambda to the 4th QCD. And now if you put together all these inequalities that I have on this slide, together with this last condition for the stop of the rolling, you get the following cutoff. Okay, you get this condition. The algebra is pretty easy to go through if you want to do it. And if you put it in the numbers, if you put in lambda QCD and you put in the Planck mass, you get that the cutoff for this model would be 10 to the 7 GeV. Okay, for decay constant f. Oh, I should have mentioned also what f is. F is In this case, it would be the axion decay constant. Pretty much what it is the scale at which like the original symmetry is spontaneously broken. By the original symmetry, I mean like the axion, I will get to that also in a second, the axion will be the Goldstone boson of a U1. So the scale of spontaneous symmetry of this U1 is this F, okay? I'm putting here some more numbers on this slide. So if you have this cutoff, lambda 10 to the 7 GeV, which by the way would be not bad at all, you get like this coupling G that I had in the other slide to be 10 to the minus 33. So it's incredibly tiny, okay? So somebody might be even bothered by this number. I will tell you in a second that in principle you shouldn't, but then I will tell you in 2 seconds that actually you should. And another number which is worrisome, and I will not get into any of the worries related to inflation, but just to mention that, is that with this cutoff and with this game in this model, you need 10 to the 50 e-folds of inflation. And remember that usually people talk about 60 e-folds of inflation. That's enough, for inflation to do its job pretty much. So this number here is about 50 orders of magnitude greater than what inflation needs. It's okay. It just means that inflation lasts so much longer than what people usually have in mind. But maybe it's not a problem, except that, I guess there are a lot of people thinking about also this aspect of the model. Anyway, I will leave it there because I'm worried about other things. So let me get to that. I want to get a closer look at the basic ingredients of the model. So I just rewrote the Lagrangian once again. And now, what the original authors observed is that the term with the cosine respects this discrete shift symmetry, okay? Which means that you can shift the field phi by 2 pi f times an integer, which I call k. Okay, and then they call this symmetry global, okay? And they say that the terms with g in the first line of the Lagrangian will break this symmetry explicitly. But then the point is now g can be tiny because as g goes to 0, you recover the discrete shift symmetry. So in that sense, they say that the model is technically natural. So in the previous slide, I showed you that with the model, you had g to be 10 to the minus 33. If there is a technical naturalness argument, it's fine. G can be as small as you want it to be, because as it goes to 0, you recover this shift symmetry, and then your model is natural. So it means that you have the technically natural way to set the electroweak scale if you play this game. Okay? The model that I just described actually is already excluded because the author, called the phi an axion, and they say this in the paper as well, by the way. If phi is an axion, when you stop at the wiggle, you actually introduce a strong CP problem rather than solving it as the original axion should. So the model is excluded in that sense. And then, they have other alternatives with like, let's say an axion prime, so an axion that couples to G prime dual, so like some hidden SU3. So you can play different games, and in the end of the day, you get a similar cutoff, if not a bit higher, and you have the same. The store is pretty much the same, or at least the concept of how the mechanism works. Okay, so I will not go into that. But again, so let's again say, what is this phi? Okay, in the original model, they use the axion to be phi. But what is an axion? An axion is a pseudo-Nambu Goldstone boson, okay? And we know exactly what a pseudo-Nambu Goldstone boson is, and we know how it arises. So for instance, for the axion, we know that you can start from a global Pechequin symmetry, a U1, and you can parameterize a complex field like this, like rho, which is the modulus times e to the I phi over f. So phi over f is the phase, and that will be our Goldstone boson in the end. It will be the axion. Okay, now the original U1 under which the capital phi rotates translates into a global shift symmetry for the axion. And this global shift symmetry is respected also after the spontaneous breaking of the global U1. But now the thing is that a subgroup of this global shift symmetry is a discrete shift symmetry, which I wrote already before and I rewrite here, which is this phi going to phi plus 2 pi f times the integer k. And now you can see that by definition, by the way the Goldstone boson is defined, because the Goldstone boson is just a phase, just an angle. Whenever you go 2 pi around the circle, or 4 pi, 6 pi, 2 pi times k pretty much, nothing changes, right? I mean, clearly, if you use this discrete shift symmetry in the original file phi, you see that the file phi just remains itself, simply because e to the 2 pi I is 1. Okay? So in this sense, the discrete shift symmetry is just a redundancy. It means that, you know, every time we go around the circle, we have the same description of the physics. So in this sense, this is a gauge symmetry. And then, you know, there is no operator in a local quantum field theory that can break this, this gauge symmetry. The way to see this, you know, you can try to write whatever operator in terms of capital phi. Also operators that explicitly break the global U1 PQ, they will never break this discrete shift symmetry. An example, actually, we have already in the theory of the axion, and we have already used it. So we know that this U1 PQ is anomalous, and it is explicitly broken by instantons. And these instantons generate this cosine term, but the cosine still respects the discrete shift symmetry. And you can try to write, you know, whatever terms you can try to in a local quantum field theory. You will never generate any term in the first line of this Lagrangian. Okay? So that's pretty much the main point of our work, the main point of our paper, which is very simple. So these terms cannot arise, the terms with the G phi, which are absolutely needed in the relaxation mechanism. And if you insist that you want to put them in by hand, okay, maybe you can do it, but then you have to deal with the fact that by doing that, you're actually breaking a gauge symmetry, not a global symmetry. And at that point, you know, you cannot really call the smallness of G technically natural. Okay, so again, this is the main message. I want to do just to make some brief remarks. So these conclusions are actually true for any pseudo-Nambu-Wilson boson, as long as it arises from a compact symmetry group. Okay, so it's not only true for the axion, it's true for Wilson boson in general. And I just want, you know, to reiterate on this the 3 points here that I have here, that, you know, you can make these 3 statements and they're all equivalent. Saying that the global symmetry group is compact means that if you spontaneously break the symmetry, the corresponding Nambu-Wilson boson is also a compact field, and it will remain compact also if you break the symmetry explicitly. Okay, as we saw before. So this is, in other words, another equivalent statement is that, you know, whenever you have a compact group, the Nambu-Wilson boson or the pseudo Nambu-Wilson boson will have the shift symmetry, which is a gauge symmetry of your theory. Okay, so these were the bad news. Now let's try to go back, you know, and to some positive news, and that's the question. Okay, is there a way that we can save this relaxation game? Can we do something about it? And I'm going to list 2 options. In the paper, we list 4, but the 2 that I'm not listing here are actually very likely not going to work, whereas the 2 options that I'm going to mention here definitely require some more thought, especially option 1. So if you guys plan to work on relaxions, I think this would be the slide for you. I could give you some points to think about. So one option is that the relaxion is not a pseudo-Nambu-Wilson boson. So it is a non-compact field, okay? Because in order to write the couplings with the G in your Lagrangian, the field needs to be non-compact. Okay, so what can it be? Maybe it's a modulus, okay? Because you need something with the potential which is, you know, kind of flat. Cannot be a very steep potential, otherwise the game wouldn't work. So we know of fields like this in SUSY, in supersymmetry, for instance, like the moduli. The Axion, for instance, which is the scalar partner of the axion in supersymmetry, would be one of these moduli. Can it do the game? I don't know. We don't have an answer to that. One of the problems here would be that if it is a non-compact field, very likely you're not going to get a cosine potential because this field has no periodicity. But maybe that's okay too. Maybe you can construct a model with a different back reaction potential, which is not a cosine, which is not oscillating, and it still does the job. So something to think about. And I've already said the 3rd point there, I guess. The other option could be still under the category of option 1 of non-compact fields. Maybe the relaxion is a dilaton. The dilaton being a Goldstone boson of conformal symmetry. And you know that conformal symmetry is a space-time symmetry, so it's a non-compact group. It's a Lorentz group. So if you can spontaneously break, sorry, it's not the Lorentz group, it's a conformal group. So if you can spontaneously break the symmetry and get this guy, maybe that can play the role of the relaxion. But then there are, a few questions to address. So the first one is that the dilaton would be a scalar rather than a pseudoscalar. So it would couple to GG rather than GG tilde. So it's not obvious that then you're going to generate the right potential. And then the other problem is that at least I am not aware of many or non-SUSY examples of spontaneous conformal symmetry breaking. Well, there are some trivial examples, but it's not clear that they can be good for this game. Another option could be the following. Could be, okay, let's insist that we're not breaking this discrete shift symmetry. So maybe we can have two sectors, okay? One where you have a fundamental periodicity scale, which I call FUV, and the back reaction sector, the one that produces the wiggles, pretty much, with another periodicity, periodicity F. And now you can take FUV to be n times F. So you can take the first periodicity in the UV to be much larger than the one in the back reaction potential. Now, just simply the fact that the action requires field excursion to be of order lambda over G, you need to ask that the larger scale of periodicity is larger than these field excursions. This just means that you don't want the axion to roll over, more than one period, pretty much. For the reason that I said before, the axion is a compact field, so rolling over more than one period doesn't really make sense for the axion. So you have to impose this condition. Once you impose that, and you play this game with the two sectors, it leads to a cutoff, lambda, which is proportional to this 4 pi v times n. So n is this guy that appears here, is by how much one periodicity is larger than the other. V is the electroweak scale. So you see that you cannot raise the cutoff much above the electroweak scale unless you take n to be huge, okay? And this is somewhat unappealing phenomenologically. But, okay, this slide was a bit quick, but I was quick kind of on purpose because I have an explicit example in the next slides to show how you can play this game that I just outlined here in option 2. So instead of the axion, consider a different Goldstone boson. Consider a familon, okay, phi. I still call that phi. So this is the Goldstone boson of a spontaneously broken flavor symmetry, okay? And now consider this Lagrangian that I've written here. The Y1 and Y2 are Yukawa couplings. ML is a vector-like mass for the fields L and LC, and then Mn is a Majorana mass, okay? So now this L and LC are doublets under the weak group of the standard model, but N is a singlet. And these are new fermions, by the way, so they are charged under a Z2, just this new fermion, so that you can avoid couplings with the standard model fermions, okay? Otherwise, they could mix with the lepton doublet of the standard model. Okay, so now you can notice, if you give it a little thought, that if you look at this Lagrangian and if you set Mn to 0, this Lagrangian respects a global U1 symmetry that we call U1 and L. And you can see this by assigning the following charges, as I have in the table, to the various fields, okay? So all the standard model particles are uncharged under this U1. The e to the I phi over FUV as charge 1, and then notice here in the Lagrangian that I have like a 2n here at the top, okay? And because of that, these fields n, L, and LC have charge n. This small n is the same n that I had in the previous slide, okay? We will see in a second why that is true, I mean, and how the whole thing works. Now, take this Mn to be non-zero. If that is true, I mean, if that is true, we're going to impose that, actually. So the symmetry, the U1 symmetry, which, by the way, we have already assumed to be spontaneously broken at the scale FUV, okay? So at that scale is spontaneously broken, and now if we turn on Mn, it will be also explicitly broken, okay, by the Lagrangian that I had in the previous slide. And this explicit breaking is going to generate this Coleman-Weinberg potential for the field phi, which has this form that I have here, okay? So again, we get a cosine. And the other important thing here is that we get it proportional to v squared rather than v, as in the action case. I could have more comments about that, but in the sake of time, I'm going to leave them aside for the time being, just to keep with the logic. Now, the f that you see inside this cosine at the denominator is this FUV divided by 2n, okay? So this calculation is actually straightforward. You can really compute the Coleman-Weinberg potential explicitly, and that's what you find. That's the leading term. I mean, there are other terms, but this is the important one. Now you see that the periodicity now is F, which is the FUV divided by 2n. And this is the back reaction potential. Now suppose that we have another sector, which I'm not going to bother writing down, but you can have a Lagrangian similar to the one that I have in this sector with other fields, okay? Instead of L and N, you could have other fields and concoct a Lagrangian in such a way that, again, you explicitly break this U1. But now you want to have these fields with charges of order 1 rather than n, okay, under the U1, and you want these fields to be heavy. So their masses will be at a scale similar to the cutoff of our theory, okay, the cutoff lambda. So with that, we could generate terms like this, like the two that I've written here. So you can generate a terms proportional to m squared cosine of phi over FUV times h dagger h, okay? And now you see this is the oscillatory part for the mu squared, so you can go from positive to negative. And now from here, if you have this term, you can think of closing the Higgs loop with the HH dagger, and that will generate the term in the second line, okay? So we'll just generate a potential for phi, which is again oscillatory. But now the oscillation here, because they are divided by FUV, which can be much larger than F, will give you pretty much this V phi potential pretty much will give you like a very long wave in this cartoon of the potential for phi over phi, okay? And along this very long wave, you will have these small wiggles that are given by the VCW here on top, okay? Because the periodicity of VCW is much smaller. So those wiggles will be very tiny compared to the long wavelength of this V phi. And now pretty much you can play again the same game. So you will have the field phi rolling down its V phi potential. You have to satisfy all the roll conditions that I enumerated before. And then, this field is going to stop when, again, the derivative would be 0. Okay, so it will stop on one of the small wiggles once you satisfy the condition. So if you work that out, you get this. You get that the cutoff then is going to be given by this expression for this specific model. And now you see that FU over F is pretty much n, or 2n in this specific case. And now if you plug in the numbers, as I did here below, you find that this cutoff can be of order, let's say, 5 TeV. If I take like these parameters ML and Mn to be 900 GeV, I take the Yukawas at the edge of the perturbativity limit. I want to be optimistic and push this cutoff as high as I can. And I took this n, the charge of the fields in my back reaction sector, to be 10, okay? Now you see that this behavior is n to the 1/4, which means that even if you take like really large charges, you're not going to improve so much on the cutoff, okay? You can, in principle, but it's not going to buy you much. I'm pretty much done, because I guess my 30 minutes are over, according to my clock. So this is the summary. So what I pretty much try to argue here, what we try to argue in our paper, is that the original relaxion, the original idea, it cannot be an axion, simply because the axion is fundamentally a compact field. So there is no way that in a quantum field theory you can generate terms that will make this field non-compact. Okay, it's compact by definition, pretty much. Now, if you want to insist that this relaxion be like a pseudo Nambu-Goldstone boson, you can. One way we showed that you can is, by introducing two sectors. This is what I showed in this very last example, that break explicitly this original symmetry with two different periodicities. But as I showed you, then the resulting cutoff is not going to be so high. Okay, the best that you can do is, is that you can achieve a cutoff of order TeV, okay, a few TeV. So this is maybe okay to address the little hierarchy problem. It's like you're postponing, the energy scale where you expect to see new physics just to a few TeV, okay? So maybe just barely enough that the LHC can barely discover something. But obviously, I mean, this is less ambitious than the original proposal, where, the goal was to push the cutoff as high as you could. Another possible option that I put forward in this talk is that maybe the relaxion is indeed a non-compact field, okay? So it's not a pseudo-Goldstone boson. But as I mentioned, model building in this direction requires more thought, and it's not trivial, it's not easy. So it's not clear that this is even possible. But we thought about it not so much, so this is definitely something to think a bit more about. And I want to conclude that, despite the fact that maybe I sounded negative with respect to this relaxation idea, I don't want to be negative, because I actually think this is a very clever idea. Okay, in principle, it's very simple. So maybe it would be nice, if more people thought about, ways to refine it and to make it work. Okay, that's it. I'm gonna just leave you with a list of papers that are relevant to these various discussions about the relaxation. Thank you.
Thank you very much, Lorenzo. I think now it's time for questions. But before that, let me remind you that you can, of course, ask questions via the Google Plus Q&A. So here, via Google, via Twitter, sorry, using the hashtag LAWOP. So I don't know if you guys have questions.
And how do I see the questions, Nico?
So there are some people here that in principle can ask questions live.
If I may, I have a question.
Sure.
Put it on the Q&A. So my question is if the cosine term is really invariant under the phase shift, because the amplitude of that term is dependent on the VEV of the Higgs, which depends on the mass, which should depend again on the G coupling, right? So the way I see it, if you make a shift of phi, you should also make the VEV might also change, right? So how does that get solved?
Right. So that would get solved, for instance, like in I go back. Can I go back to my slides here? I guess so. Actually, you still see my slides, right?
Yes.
I see the list of relevant papers.
Yeah, sorry. So let me go back to this, for instance. So now you see that the terms that determines the Higgs VEV, right, in this VH, is also a cosine. So that is also invariant under this shift symmetry. So now everything.
Right.
In your
No,
model,
I was asking about the first expression. I mean the original Lagrangian.
Oh, in the original
Right.
Lagrangian, right? No. So
Yes.
in the original Lagrangian, that would not be invariant. But then the question is, how can you possibly generate that term?
So there you see the cos term is multiplied by the VEV.
Here, you mean, right?
So the VEV, yes, exactly.
Right.
So the VEV, in principle, will depend on on the value phi.
Yeah, that's true.
So if you make a shift of phi, then that would also change the VEV.
That would also change the VEV, and then you're saying then not even that term would respect the discrete shift symmetry.
That's my point. Yeah.
Yeah, that sounds even worse. Yes. I think you're right, actually. Yes. The VEV definitely will depend on the field phi via the mu square term, and then yes, that would be non-invariant under the discrete shift symmetry.
Right. So then it's not natural.
If the mu squared is given by that combination, right? If it's given by this
exactly.
minus lambda squared, yes.
Right. So then you have the dependence on G over there.
Right.
Yeah.
Yes.
Okay. So there's no solution to this so far. Okay. I thought there would have been some sort of way out.
No, I think
no.
in a way people have not even addressed that. But I mean, the way we addressed it would solve that problem too, because now also the way the mu squared is generated is, or the way mu squared is defined is also respects the shift symmetry.
I see.
So if everything respects the shift symmetry, then everything is fine, because then also the VEV will respect the shift symmetry. But in this model, as it is on this slide, then it's not. It's not. I agree with you.
Okay. Thank you.
Sure.
Okay, great. You can see another question by Roberto Lineros. So his question is, can this idea work on other global symmetries like V minus L?
Sorry?
So Roberto is asking whether this idea could work with other global symmetries like V minus L.
Yes, but with the same caveats, pretty much, right? I mean, so the symmetry that we use is a flavor symmetry. So sure, you can do whatever global symmetry if you want to, as long as we insist that you have to respect the discrete shift symmetry. Because indeed, if you write a model, nothing will break the shift symmetry. But yes, in principle, you can write our model with the familon field is just an example. I bet you can do this with the U1 B minus L or whatever global symmetry you want to, as long as you cook up a model where you have both the spontaneous breaking, which I didn't even write that sector, okay, but that's easy to do, and you write also part with the explicit breaking. So then yes, then it would be a very similar game, but I bet you can do it with that as well.
I see. Okay. I have a question actually about the number of e-folds. You mentioned it's order of 10 to the 50 or something like this.
Yes.
Is that really a problem? Of course, I mean, we are used to something like 60 or something like this.
Yes.
Order of 10, but is that really, do we really have to worry about this or not? Just a...
The first order answer is no, in the sense that, I mean, who cares whether inflation lasts for a short time or if it lasts like 10 giga years as it should, like with this huge number of e-folds. In principle, that's fine. Although, I mean, it's not very aesthetic in a way, but whatever, that's another question. And I know that some people are bothered by this. So I think in principle there is not much wrong with that, but then probably you can run into other trouble, but I'm not sure about it. At least also the original authors, they definitely mentioned this in the original paper, and they say that in principle, it's okay. It's a weird scenario that we're not used to, but fine. It's just, a super long inflation period, but it's fine. Or maybe some people will come up with a reason why it's not fine, but as of now, I cannot think of any.
Okay, very good. Are there more questions? Eduardo? I cannot hear you. Okay, perfect. Yes, I can hear you.
So I just want to make sure I understand the basic complaint on the original proposal, which you have right there, right? Oh.
Yes.
Don't do that. Okay.
What happened?
Thanks.
I see what happened. Okay.
So let's see. So just to make sure, let's say you take this Lagrangian and you don't ask where the terms that break the shift symmetry are coming from, but just take G to be small by hand.
Yes. Yes.
Then is it your statement that large corrections to these terms will be generated radiatively, or what is it exactly? So you're saying it's not technically natural, but what does it exactly? What's the problem?
Okay, no, that's a good question. So if you start from this model, as you say, and you just think of this as an effective field theory, okay? And then you say, I don't know whether this shift symmetry is gauged or not. Okay, so yeah, it's true that if you write those terms with the G's, they will only be multiplicatively renormalized. Okay, so if you start with G small, it will remain small. Okay, there are no radiative corrections that are going to make it large. So in that sense, your theory is under control. But then, it's like saying you could give two definitions of technical naturalness. So one is this: is just that your parameters are renormalized in a multiplicative way, okay? And this model would respect that. And the other one is that you have a global symmetry. So in the limit that your sum of your parameters goes to 0, you recover the global symmetry. Your theory is actually technically natural.
Well,
so
yes.
In that sense, it would be fine. But then again, we know actually that if phi is an axion, if it is a Goldstone boson, we know that the symmetry is a gauge symmetry. It's not a global symmetry. So for sure, the second definition of technical naturalness wouldn't be respected. because you're not recovering a global symmetry, you would recover a gauge symmetry.
I also ask about that. So let's say that now we imagine the completion to this, putting in the axiom with some terms that break the global symmetry explicitly, right? And now
sorry, can you say that? I didn't hear you well. Can you repeat that? Sorry.
Yes, I'm saying, now let's imagine we consider the UV completion to this theory where you written in terms of the full axiom capital phi, right?
Yes, yes.
Which has only an approximate global symmetry. So apart from the instanton effects, okay, you could imagine some other explicit breaking and the usual things that people talk about, like gravity, whatever, right? Okay? So
yes.
it's only an approximate global symmetry.
Yes.
And at those scales, let's say above the scale F, you care about the not just the discrete part, the discrete subgroup, which you are labeling as gauge, but about the global part, the full continuous global part, right? So, and maybe at that point you can use the usual arguments of taking the naturalness, so you have an approximate symmetry that protects certain parameters. And then below the Peccei breaking scale, okay, you remain with this transformation, which is really not doing anything to the original fields, right? Which is what you mean by gauge. But at some point, this full global thing was buying something to you, it seems to me. And then if below that you don't see any large right-if corrections, then I'm not quite sure I see that there is a big problem here. So I'm trying to
fine, but if you want to do this, right, as you say, if you want to start from the UV theory, which I'm totally happy with, and first you write things in terms of the capital phi, then you have to tell me what term you can write in the UV that in the low energy will give you this G
no,
phi.
I agree. This is an important question, but also it seemed to me, from what I remember from their paper, they only require this V of G phi, right? It didn't have to be this. So this linear plus quadratic and so on could be just some Taylor expansion. It was not important or super important that. So maybe your examples fall into that category. They are so you generate in a concrete way the explicit breaking terms, and I don't know if maybe they can be understood as some expansion where it's these linear terms and so on that are playing some important role.
No, actually, no. The point that I'm making is that in a quantum field theory, if you start thinking about the capital phi field, there is no way that you're going to generate these terms for the small phi, the small phi for the axion. So, it's like if you start from the UV, whatever
these terms these terms means you will generate no potential V of some small G times phi, small phi.
Right. The reason why you cannot generate them is because if you have terms like G phi in the potential G phi square, that breaks that periodicity. So it's the same statement again. Like phi is a.
But there was a theory that was explicit breaking, right? So
but explicit breaking again, like you can try to write whatever operators you want. You can write explicit breaking operators in terms of capital phi, right? And it's very easy. You can do that.
Yes.
And if you do that, all these operators will respect this shift symmetry. So everything in the end of the day will be given in terms of cosines or sines of phi, where phi is the axion. You can try to write down whatever operator you want.
That's what I'm saying when saying that it seemed to me that in the proposal it was not really, they just need some potential that depended on G times phi.
Yeah. But in the proposal, they don't want to think about the UV theory at all. They just say, we just do the low energy, right? And in that sense, again, the only thing that I can agree with is, as we were saying before, that if you write those terms, they will not be corrected radiatively, or not much, right? Because it would be some multiplicative renormalization of those terms. So it's fine if you impose that G has to be small by hand, it will remain small. It's stable under quantum corrections. That's okay. That I will give you. But then, you know, for this model, you really need like this ingredient. For instance, you need some field that couples to GG dual. So the only examples that we can think of is like Goldstone bosons, right? That do that kind of stuff. And if you, as soon as you think of a Goldstone boson, you know where it comes from, and you know that it is compact, and you know that there is nothing in your quantum field theory that can generate those terms that make it non-compact.
So let me just to wrap up. So is it fair to say that your criticism is not so much that G is technically natural or not, but that they have not provided a way to get these kind of terms that are necessary for the mechanism. So you need some UV completion, and then you claim you will not get these things, right?
Yes and no. So my complaint is actually that G is not technically natural in this model, because in order to get, at least to get like the cosine term or so, I mean, we know how to get that from a Goldstone boson, from a PNGB.
Might as well be the property that is multiplicatively renormalized. So it's so that's what was important for their application, right? That they may have to take G to be 10 to the minus 33, but so what? Once you do that once, it will not get large corrections. That was the important aspect for their proposal, no?
True, true, definitely. But then, you know, this argument of technical naturalness kind of breaks down in a way, in the sense that, you know, now with G you're breaking a gauge symmetry rather than a global symmetry. And then, you know, fine, then you are explaining like the hierarchy problem with the crazy number, which is 10 to the minus 30 or 10 to the minus 33, which is not justified anymore.
But it is not justified because you have not seen how to get this term from the UV completion, not because. Okay, it doesn't matter. Maybe it's just definition.
Yeah. I mean, it becomes, yeah. I mean, for instance, like for the UV completion, what they also mentioned in the original paper at some point, and people, you know, keep also talking about this. They can say, okay, we can think of some kind of Axion monodromy, for instance, which is this mechanism in string theory involving D-branes, which I know very little about. That indeed, you know, where you have this Axion, which becomes non-compact. But, okay, first of all, I don't understand the mechanism in string theory. It's not clear at all that it has like a straightforward or acceptable interpretation in just quantum field theory. And another way also of stating this problem is that if you have to claim like some string theory to provide something that will give you this potential in terms of G phi, first of all, it's a bit of hand waving, one, and two, it's like if you need to say that string theory will give you this, well, string theory might as well solve the hierarchy problem to begin with. So you're not looking anymore for a solution of the hierarchy problem just within the framework of quantum field theory. You're doing something else. You're going beyond.
Yeah, but it might be that string theory is just giving you this mechanism or something. We don't know that. I mean, again,
that's fair. No, what they're saying is totally fair. Yeah, it's yeah, maybe there is a UV completion indeed that can give you something like this. And what we're saying is that UV completion will not be a compact pseudo-Nambu Goldstone boson. Pretty much, I think that's our statement, a way to put it. And maybe there is another UV completion where phi is a non-compact field that will give you in the low energy this kind of Lagrangian, and then the mechanism goes through, and that would be wonderful, actually.
All right, thanks.
Sure.
Okay, thank you. I can see a very last question from Diego Restrepo. He's wondering about the two fields, the L and N, that you introduced. That you want them to avoid mixing with the standard model fermion via this Z2 symmetry, right?
Yes.
So is the lights of these guys also stable because of this Z2 symmetry?
It is actually, which is in principle it's a nice feature of the model because there will be a WIMP dark matter.
Mm-hmm.
So this is indeed, like if you look at this model, this is exactly the singlet doublet model of dark matter. It's also well studied in the literature. So that's exactly what it is. I mean, so in the singlet doublet dark matter model, they introduced this L and LC, the doublets under SU2, and the singlet N. And then, the lightest neutral state is stable because of the Z2 and the good dark matter candidate. It's a good dark matter candidate because it's a WIMP, right? I mean, this is all at the electroweak scale, so it has weak interaction. Then it's the usual, WIMP miracle, freeze out.
So these guys will lie in the GV scale or something like this, TV.
Yes, exactly. Around the TV, slightly below, probably, let's say 500 GV, in that range, definitely, yes.
I see.
It would be a WIMP dark matter candidate, yes.
Very good. So I think there are no more questions. So thanks a lot, Lorenzo, for a very nice webinar.
Thank you, guys. Thanks a lot.
Can I ask you one more quick question?
Yes,
definitely.
So in the fact, maybe one or two slides after this one. No, let me see the slides.
Yes. Sorry, two slides after this?
Maybe. So where we put the final expression for lambda in this model at 5 TeV and some.
Yeah, this one.
So the reason there that you don't consider the ML and MN to be larger in order to increase lambda is that because you want them to be below the cutoff scale, so some self-consistency condition, or why? So I increase ML and MN.
Yes.
I think it's lambda, but only to the fourth root.
Yes.
So you took 900 GeV because that makes it kind of self-consistently below the cutoff. Is that the idea, or?
Yes and no. Actually, the issue is a bit more subtle, so the quick question might be a bit longer. So the point is, it's something that I mentioned very quickly in passing. If you look at this slide here, you see that you have this V squared here, dependence of the Coleman-Weinberg potential in the back reaction potential. Yes. So this is actually an issue of this model and of all the other models that also are in the other papers, in the sense. Because as I mentioned, like the original Axion model is excluded anyway because of the strong CP problem. So what you have to do is you always have to couple this Axion to like a hidden sector. As here we couple like the familon to, let's say, a hidden sector, right? These states that are charged under a Z2. So usually whenever you do that, you get that the back reaction potential, instead of being linear in V, is quadratic in V. Which means that I can substitute V squared. Actually, you can see this explicitly if you do the calculation by keeping the Higgs explicit rather than the VEV. You see that this V squared will be replaced by H dagger H. And that means that here again you can close the Higgs loop from this potential, and then you would get a contribution to this back reaction potential also before electroweak symmetry breaking. And now you want to make sure that that contribution, so what I'm saying is that you have the wiggles also before the field phi goes through the point where the mu squared terms goes from positive to negative. So where mu squared is positive, you still have these small wiggles because of this. And then, you have pretty much to make sure that your theory is under control, so you want to cut the quadratic divergence of this Higgs loop with something. And there is a long song and dance. Actually, we write this in a paragraph in the paper that tells you that then all these states better be like below the TV scale, ML and MN. MN especially. ML could be a bit larger, but MN, the Majorana mass, has to be definitely not larger than that, than what I have on this slide. So I was kind of quick. If you have all the reasons to be confused.
No, just say it in different words to make maybe I didn't understand that. So the reason you get this TV scale for these new states is closely connected to the hierarchy problem in the sense of quadratic divergences in some sense.
Yes, definitely. Yes, it is. It is for sure for MN. MN, the way you can cut these quadratic divergences, or the way you don't want to introduce these quadratic divergences, well, you have them, you have to cut them, is to make, by making MN light, pretty much. And the way we do this in the paper is by introducing actually another state that we call NC, and then this Majorano mass is given by a seesaw mechanism, so you have to work a bit harder. And then at the end of the day, there is this other mass parameter in the full Lagrangian where we add another extra state, which I haven't written in these slides. And that would be what cuts the Higgs loop, pretty much, what cuts the quadratic divergence there. And as a consequence, this Mn that is given by the seesaw mechanism will have to be lighter, definitely lighter than a TeV. Whereas ML could be a bit larger too, but then the other thing is also remember that these guys are stable, at least the lightest guy of the combination of L, LC, and N, the neutral guy, and that would be dark matter. So if you make it too heavy, then you run into problems with like dark matter abundance, pretty much, as well. So that's yet another reason why you cannot take these guys to be too heavy.
All right.
Okay, so I gave you a long answer. The short answer pretty much is, yeah, it's related both to the hierarchy problem, okay, because if you take them too large, you wouldn't solve it for this issue of the Higgs loop that would give you an extra contribution to the wiggles. That's the first point. And the second point is also the dark matter, you would get overabundant dark matter if you make it too large.
All right, thanks.
Sure.
Okay, so thanks, Lorenzo, again.
Sure, thank you, guys.
You guys enjoyed this webinar. So let me remind you that in 2 weeks we will have a webinar by Diego Aristizabal. He will talk about leptogenesis. And yeah, hope to see you soon. Thanks a lot.
Bye, guys. Thank you.
Ciao. See you.
Ciao, Nico. Bye-bye.
Ciao.